Hello, Mr. Cohen, can you hear me?
I can, although not very loudly. I'm using a different computer. Let me see if I can turn the volume up a little bit here.
It's probably
Yeah.
my mic. My mic is starting to go, I think, because it's not just you that has this problem with me. So,
Well, I think, I don't know if I want to try it now, but I have external speakers that if I use them, I can hear a little bit better. Let's try it as it is now. And if it's too low, we can just use the phone for the audio for the whole session.
okay, yeah, I have another headset. I don't know if that one works. This one was working better, so I don't know.
Can you hear me okay?
I can hear you fine. Yeah.
Okay, I think I can hear you well enough that we can do this. So we're in integration and Riemann sums, huh?
Yeah. And actually, quite frankly, I mean, it's kind of hit or miss. The last material is tougher, but not too bad. But I totally got, this is very similar to like doing a limit definition of a derivative
Oh
versus
God, don't tell me that. That's a nightmare.
versus taking just a derivative, right? So the Riemann sum is a very mundane, labor intensive way to take the integral of something. I'd much rather just take the antiderivative. But anyway.
Yes, unfortunately, they insist on sending you through this introductory part. And there's the hard introductory part and there's the easy introductory part. I don't run into the hard very often, and I don't expect that you're going to have to do the hard either. Colorado schools don't typically do that. Are you familiar with left ram, mid ram, and right ram?
Is this with regards to Riemann sums?
Yes.
If this is the same thing, we call them left, right, and midpoints.
Yes, okay. That's exactly correct. And let me just demonstrate real quickly. If I had a curve like that, and I want to know the sum or the area under that part of the curve, from A to B, then I'm going to break it up into rectangles. And when I break it up into rectangles, I can make it left, which usually underestimates it, because notice what happens as long as the function is rising, then the left underestimates the area under that.
Right, right.
If I were to do on a rising function like this, if I were to do the right Riemann sums, then I would choose that as my starting point. And then the next one would be like that, and so forth and so on. And you can choose that you can see that the right endpoint overestimates. Yeah.
Right.
As long as it is a increasing function. It's the opposite if it's decreasing. If it's decreasing, the left hand overestimates it and the right hand underestimates it. And you can also use middle. So you make your rectangles and you make the very middle and draw your rectangle about that. And then the next rectangle would go about there. And so for the middle, that one would be like that. And you can see that the middle is going to do a better job than the left or the right in general, because it underestimates part of the rectangle and overestimates the other. So in terms of actually approximating what the area under the curve is, the middle is usually the best one to use.
Right.
And there's all kinds of them. There's not just rectangles, there's trapezoids. So that instead of using rectangles, you would use trapezoids. And you can see that that would estimate the area much more accurately than the left, the right, or the middle.
And that makes sense, because that's basically just a triangle with a rectangle.
It's a trapezoid. So instead of, but it's, oops, what happened to my, oops, I'm drawing on the wrong thing. Yeah, in other words, you end up with trapezoids instead of rectangles. And the way you calculate the area of a trapezoid is
AB over 2 plus H.
Yeah, in other words, it's whatever the formula is for a trapezoid. And a trapezoid, usually you're looking at trapezoids and they look like this. But when you're talking calculus, they're always vertical. So they're never going to look like this. In other words, they're always vertical, like I've drawn this one here. And the area of that trapezoid is the average base. The lower base is f of a. The higher base is f of b. So you add them together, divide by 2, and multiply that by the distance, the width of the trapezoid. And that gives you the area of the trapezoid. Before I go any further, I want to be really clear you understand one point about calculus and integral calculus in particular. And that is this concept that this is the x-axis and this is the f of x axis. And with calculus, it really pays to use function notation here as opposed to y. Because what is this point right there?
The f of x.
It's f of a.
F of a, okay.
And what if I put a second point on there and I try to figure out where that is? That is f of b.
Okay.
And this is a gigantic concept because you don't always have numbers for a and b. If a was 2 and b was 3, then it would be f of 2, f of 3. But in terms of the theoretical stuff for calculus, they usually leave it as f of a and f of b. And in fact, the same concept applied to the derivative quotient definition, because one of them was f of x, the other one was f of x plus h. And how do you get the slope of that? You do f of b minus f of a, all divided by b minus a.
Okay.
In other words, if I indeed wanted the slope of that line, it would be f of b minus f of a. That's the rise. And the run is b minus a.
Okay.
So that's how you'd always get the slope of that. So if you're just dealing with left endpoint, mid, and right, then let's go at it. I can help you easily.
Okay, yeah, so
go ahead. Well, there is actually a more difficult definition for integral. That has to do with these summation formulas and
Yeah, so that's what I wanted to. There's a question that I had for integrals, but I wanted to spend the majority of the time with Riemann sums, particularly notation, and what we're trying to do in class, or what the teacher's asking us to do, is to take something in Riemann sums get it to where I can take the limit definition as it goes to either infinity or zero, and do the algebra essentially to show that.
Okay.
It's not too terrible for the algebra half, but I always get lost on how to take it. So I guess with that, the way, I don't know what you're familiar with, it's not super different from what I've seen on the internet, but you usually have something like n sigma I, or we use k in class, equals 1.
Yeah. Okay.
And then your function.
Let's go there. I can help you with it. It's not my best. It's not my forte. And the reason it isn't is because it's only like once every 3 years that a student gets it taught calculus at that level. And as it so happens, I had a student 2 months ago that she was taking the Saxon course for calculus, and she covered all the hard stuff and all the medium stuff and all the easy stuff. And I'm not a big proponent of that. To me, I would not cover this area. I think it's actually beyond the scope of an introductory calculus course. I'm sure you're aware of Saul Kahn. He says the same thing about the delta epsilon definition of limits. He says, yeah, you can teach it, but it is beyond the scope of most people, and it'll just demoralize calculus students. But let's see if we can make some progress with this. If I'm going over stuff you've never heard of, please tell me and I will stop immediately, because the last thing in the world I want to do is go over this stuff if you're not actually getting it. By getting it, I mean if the teacher isn't insisting on it. Let's start with this. Does this look familiar?
Yeah, so this is good.
Okay. These are summation formulas. And in order to attack area under curve by the Riemann definition, you need these. All 4 of them.
Mm-hmm.
And so let's go through how these work. And that's the best way to do it. It really is, in my mind. I may have to do this. Yeah, my photograph didn't go all the way down here, so I'm gonna have to write it out, but that's okay. Let me do it that way. And I think even if you have some problems with that require us to do it this way, it's best to start with this. So this is usually I going from 1 to n. I, incidentally, is always an integer. It's never 1.5. So if it starts at 1, the next one is 2 and 3 and 4 and so forth. So if I wanted to know what this becomes for n equals 10, 100, 1,000, and 10,000. How do I do it? Well, if we go back here, let me just go through it. First of all, and this is really hard to understand, n is not a variable. Because it is not a variable, I can take it outside the sigma. So this whole thing that I've written, let's hold on, is equal to 1 over n squared times sigma of I plus 1. And I won't bother to put the I equal 1 to n on every one of them. It's just to save time. And what that's equal to is, because there's a sum there, and when you have the sum of the sum, you can separate them. So it becomes 1 over n squared times sigma of I plus 1 over n squared times sigma of 1. And do you have these summation formulas in front of you? So I don't have to keep referring to them?
Yeah.
Okay. As long as you have them in a book or something where you can follow what I'm doing here. So if you look at the sigma of I, it's equal to n times n plus 1 over 2, correct?
Correct.
Okay, so this thing now becomes 1 over n squared. I'm going to have to start writing smaller because I'm running out of top space here. And in place of this, excuse me, there's no sigma anymore because we're applying the summation notation. So this becomes n times n plus 1 all over 2. That's what that is equal to.
Mm-hmm.
And this is equal to just n. So n over n squared. You with me?
Yeah, yeah.
Okay, and this becomes 1 over n squared times n squared plus 3n, if you just do the algebra, all over 2. And the whole thing comes, now if you completely do the algebra, you end up with n plus 3 over 2n. So this thing that we started with up there is equal to that. And if you want to know what it is when n equals 10, you plug it in. If you want to know what it is when n equals 100, you plug it in, and so forth. In other words, for n equal 10, then this thing would be 13 over 20. This right there.
Okay.
If you want to know what it would be when n equals 100, it would be 103 over 200. If you want to know what it is when n equals 1,000, it's 1,003 over 2,000. And 10,000 becomes 10,003 over 20,000. And you can see that as n gets bigger and bigger and bigger, what does this thing approach? In other words, what is the limit of this as n goes to infinity?
It's infinite.
As a straight limit problem, forget everything else we've done. Just what's the limit of that as n goes to infinity?
It's infinity, right?
It's the ratio of the coefficients of the n term.
Oh.
So it's 1/2.
1/2.
And you can see that that thing is going towards 1/2, right?
Okay.
The bigger n is, the closer it gets to 1/2. So that is the essence of summation notation. Is first of all understanding this page right here. on how you would do a theoretical problem like that. That's not necessarily a Riemann sum or anything. It's just what would the sum from I equal 1 to n be of I plus 1 over n squared. And that sum is 1/2. Because usually this is, you're doing the limit as n goes to infinity. Certainly with integral calculus, that's what it's always based on. Because n is usually the number of rectangles that you have under your curve.
Okay.
And as each rectangle gets thinner and thinner and thinner, you have a bigger and bigger and bigger n. In other words, if I want to pick big fat rectangles, I don't have very many of them. I only have 5 of them. And the width of them is this distance. Since I put 5 of them in there, is that distance divided by 5. But this gives me an approximate answer, depending on whether I'm using left-hand endpoints or right-hand endpoints. I'm using right-hand endpoints, it gives me quite a bit of extra area there. But if I let n go to infinity, then what I'm doing is I'm putting a ton of these rectangles in here. I'm putting infinite number of them.
So n represents the number of intervals.
Yes, the number of rectangles that you are filling up this area under the curve. In other words, this is the way they did it for thousands of years. Back in the Roman times and the Grecian times, this is all they knew, was that they could figure out the area under the curve by putting rectangles in there. And the more rectangles they put in there, the more accurate they got. And that wasn't calculus, that was geometry. Okay.
Quick add here.
Uh-huh.
And maybe this was more about the notation than the formula per se, but, and actually I think that's what the n over n, the 1 over n squared is doing. That would be our delta x, right?
Delta x is the width of each rectangle.
Okay,
so as n goes to infinity, delta x goes to 0. You'll notice that delta x is right here. That's delta x. And when I put a bunch of rectangles in there, delta x gets much smaller, right?
Mm-hmm.
So if I put an infinite amount in there, delta x is actually approaching 0. And this is the concept of calculus, is that delta x, you're never dividing by 0, but you're dividing by a number that's always getting really, really close to
'Cause
0.
my professor has, like, this is the general formula. Maybe that's not the best way to word it, but you know, so you would have something like n sigma I equals 1, and then f of x, where f of x equals x I star times delta x.
Yeah. Well, we haven't got to the hard part
yet. Okay.
I've given you the easy part so far, but let's talk about a real world application where they actually give you a function and they want you to figure out the area under the curve based on this definition, this Riemann definition, which is quite different than any other way to do it. You were very correct in surmising that this is a lot like the limit definition of derivative. It's the hard way. Once you figure out the easy way, then all of this goes into the past and you don't ever do it again. And the easy way is just the antiderivative.
Right.
In other words, it's kind of like the power rule in reverse. for simple functions. But for complicated functions, figuring out the integral is really, there are not 4 rules. You know how in differential calculus, you have the power, the product, the quotient, and the chain rule? And between those 4 rules, you can differentiate any function that I can give you, no matter how complicated. By a combination of those 4 rules, you can differentiate. Well, integral calculus, even though it's the inverse of differential calculus, is not that easy. It is like an order of magnitude 3 times more difficult, at least, maybe 10 times, in doing integrals, even in finding antiderivatives. And in fact, well, I guess I can erase this for this point. If you followed all of this, we'll go to the next step here. But there are some interesting things that you're probably not aware of. You recognize what this all means?
Yes.
Okay. That function has no antiderivative. There is no function in the universe whose derivative is this. So we have to figure out a different way to find the antiderivative. And this is actually like Calc C, how you would do this. You would approximate this function by power series, and then you would integrate each of the power series, and you would have an infinite series that was an approximation to the integral of that function.
Okay.
There is no exact answer. It's all approximations at this level. But we're getting ahead of ourselves here. I'm just trying to point out that it's probably not as easy as you might think it is. In other words, if I say, what's the integral of this? Well, that's a piece of cake. Because all I do is use the power rule, which means I add 1 to the exponent and divide by the new exponent.
Third over third.
Super easy. But if they want you to use the Riemann sum definition, well, let's go through one of those. If that's what you want to do.
I don't want to do it, but I
Good answer. I wish you didn't want to do it either, because it's one of those things that I kind of understand about 80%, but I've got some pretty good examples here in the book.
Yeah, we could just do simple functions. I just,
yes.
Because basically, and correct me if I'm wrong, you know, it's my teacher, I think, kind of gave away the answer, but she said that the right endpoint formula for this Riemann sum is the easiest.
Which is I times 2 over n, which is 2i over n.
Okay.
And the left hand is 2 times I minus 1 over n. So let's take a simple function. F of x equals x squared. And I'm going to draw that over here on the left. And that's just half of a parabola if I'm only considering positive x's. And let's say that I am going to divide that into 4 rectangles using left hand. And the first rectangle I'm going to put there. Next one I'm going to put there. Next one I'm going to put there. And the fourth one's going to go. And if I were to look at right endpoints, looks a little different. First of all, the first rectangle goes right here. The next one goes right there. The third one goes there. And the fourth one goes there. So you can see that because we have a function that is increasing, the right-hand endpoints underestimate the value and the left-hand endpoints, excuse me, the other way around.
Yeah.
The left-hand endpoints underestimate the area, the right-hand endpoints overestimate. And if the function was actually going the other direction, it would be the other way around.
Okay.
But here's the tricky part. And I'm going to give you this, and well, let me go ahead and tell you how they figured this out, because this is probably worth knowing. If I want to know what delta x is, which is the width of each of these rectangles, then it is
over n. Right?
They want to know between 0 and 2. Okay, so here's 0, here's 2 in both cases.
Okay.
So if I wanted to know the width of that, that would clearly be b minus a divided by how many rectangles I have.
Okay.
And that is 2 over n. So if I have 4 rectangles in there, then each rectangle's delta x is a half. With me?
I'm with you. Yep.
Okay. Now, if I want to know, and this is where I might be a little limited in how I best can explain this. But if I want to know what m sub I is for the left endpoints, I would write it like this: m sub I equals 0 plus I minus 1. And this is probably the hardest thing about this to understand. And I'm not sure I even need to take the time to explain it. You might just have to take it on faith for the moment until you understand it more, and then you can actually get the concept of it. And this one, capital M for right hand. I'm looking at left hand, that's a little m. I'm looking at right hand, it's a capital M. This ends up being 0 plus just I times 2 over n. And notice that this is actually a little easier than the one above it.
Okay.
So the question is, let's figure out, using the left hand endpoints, what the lower sum is.
Okay.
Okay, so here's how it works. And let me do this in blue up top, and I'm going to write pretty small here. But if I want the sum of the areas, then it's equal to sigma sum, where I goes from 1 to n. And the function is f of little m sub I times delta x.
Okay.
And that would give me the sum of those 4 rectangles. And so what I do next is substitute the function. In other words, that means, what is the function? In our case, the function is x squared, right?
Right.
So what this is really equal to is sigma of the f of 2I minus 1 over n times 2 over n. Now, what is this? This is the height of each rectangle. this part right there, and that's the width.
Okay.
So that is going to give you the sum of each rectangle, and then we're going to add it all up as I goes from 1 to n, where n in this case is 4. Okay. And let me just go through this algebra. So I go from this step, and the next thing I do is figure out what that is. Well, it's it's x squared, right? It's the function squared. So this whole thing that I've circled becomes, and I still need a sigma, excuse me. The definition of this, in other words, I'm taking f of m sub I, little m sub I, and we've defined m sub I, this blue circle here. That's what m sub I is. So f of that is 2 times I minus 1. You love it when they use i's and ones all in the same thing. Squared, because that's what the function is square.
Okay.
Times the width of each rectangle, which is delta x, which is 2 over n.
Okay.
Now the rest is just algebra.
Right.
And let me just, I'll take it through the steps without spending the time to do all the algebra, but you can certainly do the algebra here. And what you get is you with me?
Yes. Yeah.
Whenever you have sigma notation, you can take anything that's not a variable and take it out. You cannot take variables out from the sigma. And the variables here are I. Notice that it's I that's going from 1 to n. We just haven't told you what n is yet. But regardless, n is not a variable at this point. And so I can take this whole 8 over n cubed outside the sigma sign, and leaving behind 3 sigmas that I can then separate. In other words, I have the sigma of I squared minus, I can take the 2 out, the sigma of I plus the sigma of 1. In other words, I took these 3 things that were being added or subtracted, and I turned them into 3 separate sigmas.
And again, you explain that as like the sum of the sums is the same as, I don't know exactly how that
Yeah, the sigma of a sum of variables is the same as the sigma of each variable added together.
Yeah, okay, yeah.
In other words, is all I've done is I've taken that and separated it into 3 sigmas.
Gotcha.
And the 8 over n cubed is still outside, and I took the 2 outside because it's a constant. You can always take constants out. Now is where you got to go use your summation formulas.
Right.
Because I need to figure out what that is. Well, it turns out if I pull up our summation, you've got a list of it in front of you. That's n times n plus 1 times 2n plus 1 over 6.
Yep.
And the second one is such, and the third one is such. And if I do all the algebra, and if you want me to go through all of the algebra, I can, but it's really quite tedious. But this is what I end up with.
Quick question. You don't need to go through the algebra, but for the last one, what would that be in terms of summation formula, where just it's sigma times 1?
N.
N? Okay.
Yeah, it's the one that says sigma of C.
Okay, so it's C times N.
Yeah, C times N. So in this case, it was 1, so it's 1 times N.
Okay, I got you.
Okay. And now if I do more algebra, I end up with 8 over 3 minus 4 over N plus 4 over 3N squared. And that's what S of N is. And you can see that as N, if N were to go to infinity, this thing would be 8/3 because these last two terms go to 0.
Okay.
Okay. Now, let's do it with right-hand endpoints. And the only difference is that now when I look at f of capital M sub I, I'm going to substitute this instead of this.
Okay. Okay.
Okay. Now I got a space problem here. Let me do this. Maybe you can take a picture of that or something. I am recording this session.
Let me take a picture real quick.
Yeah, take a picture real quick so you'll have it for reference, because unfortunately I can't scroll down here and get more room. Yeah. So I'm going to do it in red, doing exactly what I did on that one, only in here I'm going to be substituting 2i over n, not 2 times I minus 1 over n.
Okay. Okay.
So let me erase, and I'm going to leave the final answer there. And just redo this. Now let's do it in red. So this becomes f of capital M sub I, still times 2 over n, because delta x is still 2 over n. And that becomes sigma of 2i over n squared, because that's what you do. You substitute whatever's in the parentheses into your function of f of x times 2 over n. And this one actually becomes a little easier because the algebra isn't so hard. Notice that that 2 times I minus 1 makes the algebra a lot harder. But if you're using right endpoints, we don't need to do that. And this comes down to 8 over n cubed times I squared. Much simpler immediately. And again, I can take the I over, or the 8 over n cubed out, because n is a constant at the moment. And it's I squared. And if I do go to my summation formulas and substitute that, it's the same as it was before, where the I squared turns into n times n plus 1 times 2n plus 1 all over 6, which becomes 8 over n cubed times, or excuse me, actually, I got that wrong. It becomes 4 over 3n squared times 2n cubed plus 3n squared plus n. Sigma is gone. In other words, I used that The definition of that in summation notation is n times n plus 1 times 2n plus 1 all over 6.
Mm-hmm.
And now if I do this algebra, I get down to 8/3 plus 4 over n plus 4 over 3n squared. And you can see that there's not a lot of difference between the red and the blue. This is my S, the sum of those intervals using the right endpoints.
Oh, that makes sense. Yeah, because so that's overshooting, so that's why there's a sign difference.
Yeah, and you can see that this is going to be bigger because that's a positive number, and that is being subtracted, and that's the only difference between these two things.
Mm-hmm.
But in both cases, if I take the limit as n goes to infinity, I get 8/3 for both of them.
Okay.
So that is how you do this with a simple function like x squared.
Okay.
And if your professor says use the right hand endpoints, then use capital M sub I. If he says use the left hand endpoints, use little m sub I.
Okay.
And he may want the limit as n goes to infinity. He may want it for n equal 10, 100, 1,000, 10,000, so forth.
Okay.
But you can certainly see as n goes to infinity that these two both go to 8/3. That's the only thing that survives, is that 8/3 right there.
Okay.
And this is kind of proof that as n goes to infinity, the right hand endpoint equals the left hand endpoint. It's not as long as n is finite. They're not going to equal. Those two things at the bottom right are not going to equal one another. But as long as n's going to infinity, they both equal 8/3. And 8/3 is the area under the curve between 0 and 2. And in fact, let's do it now the easy way, just so you can put the two together. If I wanted to do this from 0 to 2, it becomes x cubed over 3 evaluated between 0 and 2. Well, what is that? That's 8/3 minus 0.
Yep.
That's the easy way to do it. Are you familiar with this? Have you gotten to that yet?
So this is actually, I'm timing this pretty well. If we can, this has been pretty helpful. If we can, I had a question I was working with a group of people with, and it is an integration problem. So, and I'm sure you'll enjoy working through it a little bit more than the rerun sum. So this is an integration problem evaluating it. It's so the function is 2 over x plus 1 squared. This is using U-Substitution with integration. And then the bounds are from 1 to 3.
Oh, okay. So we're off of the Riemann definition.
Yes, I just wanted to.
Beautiful.
I've got a test coming up this week, so we might revisit it.
You almost certainly will get a maximum of one problem that wants you to do it this way.
Right.
Before we leave this subject, let me just change one thing really easily. If I made the function x cubed instead of x squared, then the only thing that would happen is I would go over here and I would cube that.
Okay.
Or down here, I would cube that. In other words, I would still substitute capital M sub I and then perform the operation. And the function is cubing it. So that's what you do. So no matter how complicated the function is, you can use this method to find the area using the Riemann definition.
Okay.
So if I had x plus 1 squared over 2, that's what I would substitute in for f of x plus 1 squared over 2.
Okay, cool.
All right, let's erase this. And let's see, you said 2 over x plus 1 squared. Correct?
Correct. So I've learned integration as the fundamental theory of calculus.
Okay.
That's what the subject.
Yeah, the U-substitution is the first really thing that you learn that's not just the power rule.
Right.
In other words, you can't really use the power rule on this.
Right.
But what you can do is use substitution. And do you have limits on this, a lower and an upper limit?
From 1 to 3.
Okay. And notice that you don't ever have an integral without a differential. If I didn't have that dx in there, this thing would not make any sense.
Right.
Okay. So if you're doing U substitution, usually you let the U equal to the complicated part. Like that.
Right. Right. And then du would equal 2.
Du dx, let's start there, equals 1. So therefore, du equals dx.
Okay.
And I can rewrite this integral in terms of u now. And I'm going to leave the limits off for a moment, because when I do it as an integral in u,
the bounds change.
The bounds change. We'll figure that out from there. But let's just take it one step at a time here. And I can replace du with, or dx with du, based on that. Okay, so now this is a form that I can integrate quite easily using the power rule. In other words, this is the same as 2u to the minus 2 du. And so I'm going to take the 2 out just for clarification on doing this first one.
Make it simple.
You don't actually have to do that every time you have a constant. But what we have left over, in other words, what that is u, we add 1 and divide by the new exponent. I still have my 2 out there like that. And I'm going to evaluate this at the new limits of integration. Well, when x was 1, u was 2, right?
Right.
Based on this up here. So instead of going from 1 to 3, I'm going to go from 2 to 4.
Right.
When I turn it into an integral of u.
Okay.
And now you know how to evaluate these. You just 2 times. You always start at the top one and subtract the other one.
Right.
So the top one is a negative 1/4. Correct? Did I do that right?
Well,
minus the bottom one, which is a negative 1/2.
Why is it minus 4 times 1/2?
Because when you evaluate these, you always do the top one. In other words, f of 4 minus f of 2, where f is this thing.
Right.
So if I substitute 4 for u, what do you get? You get 1 over minus 4. In other words, you get that. And if I substitute 2 for U,
I'm sorry. So you have 2, which is the constant we pulled out, times and 1/4 minus 4 times.
Good catch. Good catch. I actually need, yeah, there's no 4 there. In other words, I should have written it like that.
Okay.
Correct?
Yeah, correct.
And this represents this with 4 substituted for U. And this represents that same thing with 2 substituted for U.
Right.
If I do the math, all of that gets replaced with a positive 1/4. So that thing is 1/2. That is the area of that function between 1 and 3.
Let me take a picture of this, because I was working on this with a group, and like we were getting. I see where we went wrong. We were close, but we just could not. The internet was telling us it was 1/2, and we were getting 4/15.
Yeah.
But now I see why.
Okay. Good.
So yeah, that's cool.
Yeah.
Okay. Awesome.
There's some other U-substitution problems that are there's actually 2 types of U-substitution problems. This is one of them. Another one involves pattern recognition, where you have a composite function. You've undoubtedly had those. Did you take a picture of this?
Yeah, so let me ask one quick question though.
Sure.
Or maybe a couple, let's see. So backing up a couple of steps, you took out the constant with the integral of U to the -2, which is the same as how it was rewritten before, with the U on top in the numerator.
Yeah.
That then became 2 U-1/1. How does that stuff work? Because that's
when you are using the power rule. In other words, if I want to integrate that right there, my first step is to always add 1 to the exponent, which gets it to -1. And then divide by the new exponent.
Yeah. Okay.
So I added 1 to the exponent, and I divided by the new exponent.
Okay.
And whether I don't need to really take that 2 out, I just did it kind of for clarification. I could have left it in there and just multiplied it and done the whole process, multiplying both of them by 2. I think for understanding it, it's a little bit simpler if I do pull the 2 out. And it's good to know that you can always pull constants out of an integral sign or a sigma. Same thing. The integral sign is sigma. That's how it got. They took sigma and just smoothed it into an S.
Yeah.
It's the same thing though. It means summing everything up
under the curve.
Under that curve of this function. If we were to put this function into Wolfram alpha, I don't know what it would look like. It would be some hyperbolic function. So it would probably look something like this. And if I want the area under the curve from 1 to 3, then this is the way to do it.
Yep.
The problem is that you cannot apply the power rule directly here.
Right.
If this was something simple like x cubed, then I don't need to use U-substitution. And there's another one that is really quite cool. See if I can remember how to do this one. This also requires U-substitution. It's called change of variable. There's 2 types of U-substitution. There's the U-substitution that we just used, which is called change of variable. And then there's the U-substitution where you have two functions. I wanted to do this one, but yeah, let's finish doing this one. I don't have a good way of taking that integral without U-substitution.
Okay.
So I'm going to let U equal x plus 1. That makes du equal dx. And now I'm going to go back in there and rewrite this thing as a function of u. Well, if u equals x plus 1, then x equals u minus 1. Correct?
Correct.
Based on this.
Mm-hmm.
And now, the reason this is so much better is because I can now integrate this. Because I have a single entity in the denominator, I can split that thing up into the two fractions.
Okay.
So it's the integral of 1 minus the integral of 1 over u. And this is pretty simple to do. The integral of 1 is always whatever the variable is. And this is the natural log. Evaluated from wherever to wherever.
Oh, yeah.
Now, you don't necessarily have to change the limits of integration. You can do it one of two ways. The last problem we did, we changed the limits of integration. Instead of going from 1 to 3, we figured that u went from 2 to 4.
Mm-hmm.
But the other way to do it is just before you actually evaluate the answer, you go back and resubstitute. So instead of u, it's x plus 1. And instead of the natural log of u, it's the natural log of x plus 1. And so because I went back and changed it back into a function of the x instead of u, then I can use the old limits of integration. Let's say this was going from 1 to 3. Well, because I've substituted back for x, I can do it from 1 to 3.
Gotcha.
If I wanted to leave it in u, then I would have to go from 2 to 4 again.
Okay. Okay.
I find this is actually the easier way to go because you don't have to go through the math of doing that. In other words, I always substitute back for u before I do the evaluation.
Okay. Okay.
And this one is clever because that is a binomial, I cannot split this into two fractions. That is not x over x plus x over 1. You can't do that. A over b plus c is not a over b plus a over c. But once I use U-substitution and I get it like that, where I have a single denominator, a single thing in my denominator, now I can break it up into two fractions. And instead of the integral of this, it's the integral of that minus the integral of that. And each of these is easy to do.
Okay, so basically, if you change the variable, you have to change the bounds. But if you leave it as the old variable, you don't have to.
If you leave it as the u variable, you have to change the limits of integration.
Okay.
If you change it back before the evaluation, in other words, I get to that step. But the final step is the evaluation down here. And I went back and resubstituted for u. And instead of u, I put in x plus 1.
Gotcha.
And so because I resubstituted back and turned it back into a function of x, I can use the old limits of integration.
Okay. Okay.
The alternative would be quite simple. It would just be u minus the natural log of U evaluated from 2 to 4. Going to give you the same answer.
Okay. Okay. That's cool.
And I have yet to find a problem that actually requires you to change the limits of integration. Every problem I've come across, you could always substitute and turn it back into a function of X before you did the evaluation. The evaluation is this part here, where you evaluated the lower and upper limits of integration. Now, before we leave, I want to just go over one last thing. That is U-substitution called change of variable. There's another kind that is like this. And in order to solve these, you have to get kind of good at pattern recognition. And here, I'm going to use U-substitution just to show you how this works. In other words, it's always what's on the inside that you're substituting. You with me?
I'm with you.
So du dx is 2x. So du equals 2x times dx. And you'll notice that I have a 2x and a dx all in the numerator. So I can substitute, there's my 2x dx. So I'm going to take this 2x and this dx and put in du. So it's now going to be the cosine of u du. You see how I got to that step?
Yep.
Well, I can certainly integrate that. That's the sine of u. Which means the answer is the sine of x squared.
Mm-hmm.
And depending, if I was going from 1 to 3, I would do it this way. And if I was evaluating it in terms of u, well, if x goes from 1 to 3, u goes from 1 to 9.
Right.
So if I wanted to evaluate it, it would still be the sine of u from 1 to 9. Both will give you the same answer.
Okay.
Because notice that when I substitute the 3, I get the sine of 9.
Right.
This is the more normal kind of U-substitution, is when you're looking at a function like that.
Mm-hmm.
And what you're looking for, always, they call it pattern recognition, because that's really what it comes down to, is look for the derivative of the inside as a multiplier. In other words, because the inside is x squared, the derivative of that is 2x.
Mm-hmm.
And I've got 2x as a multiplier. If I change this to 2x cubed, I can't use U-substitution anymore. It won't work.
Huh.
In other words, whatever the derivative of that is, has to be the same level of exponent as this. Doesn't have to be exactly 2x. I could make that 3x and I could still use U-substitution. But this has to be the same degree as the derivative of that. And the derivative of x squared is 2x. So I need an x as a multiplier. And this one is what is usually referred to as U-substitution. Whereas the other one is still called U-substitution, but it's called change of variable.
And that was true for the problem that I showed you as well. That's a change of variable. Is that?
Yeah, the one you gave me was the change of variable.
Okay.
Whereas all I had to do was take that denominator and let it equal to u and figure out what everything else was. And then I ended up with an integral in u that I could actually integrate. I couldn't integrate it as long as it was in x, because I have no way, I don't know how to integrate this. That we don't have any way to do that.
Okay.
But once you turn it into u, change a variable, now we can do it. And the same thing up here. I can't really integrate 2x times cosine of x squared without doing some sort of a u substitution. And the u, the best way to always start these is not necessarily to recognize that, oh, I can tell that the derivative of that is 2x and there's my multiplier. That's what you're always looking for. But you don't really need to see it. You just need to know that if I'm going to do u substitution, I want u to be whatever's on the inside. Gotcha. Make that x squared minus 1 over 10, and that's what u is.
Okay.
And the majority of your problems are going to be that. The change of variable is actually quite simplistic. And once you figure it out, they don't give you too many more like that. But you get tons of these where you have two different kinds of functions being multiplied together. And one of them is the derivative of the inside of the other.
Okay, so pattern recognition is.
Yes, it's pattern recognition. It would be the same thing as if I wanted to take the integral of x cubed minus 1 dx. Well, that's really hard to do. But if I look at the inside and figure out what the derivative of that is, it's 3x squared. So if I happen to be multiplying that by 3x squared, now I can do it really easily by using u substitution, letting u equal to x cubed minus 1.
Okay.
And it's all because when you take the derivative of a compound or a compound function, which is what this is, I can't multiply that together. I can only represent it the way I've done it here. But it's a composite function is what I meant, not a compound. When you see a composite function and one of them is the derivative of the inside of the other, you got yourself a candidate for u substitution. And let me tell you something else. U substitution is the first of about 12 methods you're going to learn for doing integrals. Each one is more progressively difficult. The simplest one is the u substitution, change of variable, and then u substitution pattern recognition. And then it just gets harder after that. And that's what makes integration so tough, is that you don't have 4 nice little formulas that you can just use.
Luckily, that's going to be tabled till next semester when I'm in Calc 2.
That's where you'll pick up doing harder integrals. But certainly mastering u substitution is a good start.
Yeah.
Now, the reason it doesn't matter if that's 2x, let me just point out something here. Even if that was just x, I'd still use u substitution. And how would I do it? I would do it this way. I would take a 2 out and put a half in. Whoops, excuse me. I would put a 2 in and take a half out. So I haven't changed anything. Okay. And now I've made it such that that is the perfect derivative of the inside.
Interesting.
And that's a little of a tricky concept to do. It requires a little bit of thinking outside the box. You actually don't have to master this technique, but it's the technique that most people teach when they're teaching calculus. In other words, if what you find over there is not the exact derivative of that, then you can make it the exact derivative. As long as the power of the x is to the 1, I can do it, regardless of what that number is. That number could be 17. And I would just factor out 17 over 2 and make it 2x.
Okay.
Connor, is that a good place to stop for this evening?
I think it's a good place to stop. Yeah, I'll definitely be contacting you for the, within the next week or so, because I got the exam coming up and I want
Okay.
a refresher on the unit.
One thing, let me just point out, because I was having troubles with this. I didn't know whether it needed to be positive or negative, and I thought it had to do with which way it was turning. It doesn't. If this thing is increasing, then d theta dt is plus. If it is moving down like that and it's decreasing, then d theta dt is negative. I know you're beyond that part of the calculus, but in case it comes up on a final, that's how you tell. And in our airplane problem, where you had the airplane right here, and you had the receiver station right here, and the airplane was going there, and we had this angle theta, well, d theta dt is getting bigger as that airplane moves, correct?
Yes.
But if the airplane was over here, heading in this direction, d theta dt is negative because it's getting smaller.
Yeah, when I looked over that work, this is some time now, but
yeah,
what I think the issue was is that it was something about like you had secant squared, and you could multiply by secant squared to divide by 1 over cosecant squared.
Right.
And
1 over cosine. Yeah.
1 over cosine. And I think it was easier to, I can't remember what it was exactly. It was a small identity error that made it so that instead of having it, because basically if the fraction was flipped, the numbers would have been correct. The numerator and the denominator.
Well, the reason I had problems with it is because I wasn't drawing my picture correct.
Okay.
Because the explanation of the problem, it wasn't clear to me if the airplane was directly overhead of the radar, or if it was some distance out here, or if it was some place over there. Doesn't really matter, but what's really important is that you understand that depending on how you draw your picture, d theta dt is going to either be positive or negative. Just like ds, this distance right here is s. And in this drawing, ds dt is negative because it's getting smaller. In this drawing over here, ds dt is positive because it's getting bigger.
Okay.
So the way you make your drawing and understanding what d theta dt, the difference between when it's positive and negative, is really important. And in fact, all of this is. If that airplane is closing, then that distance s is getting shorter. So ds dt has to be negative. And it has nothing to do with whether it's going to the left, to the right, up, or down. It all has to do with whether that variable is decreasing or increasing.
Maybe it just so happened to work out this way, but I ended up reworking the problem because everything you did was right.
Yeah.
I just divided by secant squared.
Yes, but even that is not that easy, because then you have to figure out what the cosine is. And that's the toughest part of that problem, is figuring, because you end up with cosine squared in the numerator, and you have to go to your drawing to figure out what is the cosine of theta. Well, and if this is the drawing, then the cosine of theta is this side over this side.
So check it. This is pretty cool. So if you relate the secant squared of theta with regards to what it would be on a triangle in the context of this problem, you would have x squared plus b squared over x squared.
Yes.
And if you then took the cosine squared of theta, you flip that around, which then gets you everything to the correct place.
Yes.
So that's
the toughest part of those problems.
Yes, it really was.
It is, absolutely. I mean, well, the toughest part is differentiating both sides and getting secant squared on the left and then figuring out what to do with it.
Right.
And you have to do that. You have to turn it into 1 over cosine squared, multiply both sides by cosine squared. You end up with cosine squared in the numerator, but then you have to go in and look at your drawing to figure out, well, what is the cosine of theta in terms of x and s and all of those variables?
Yeah, I got to be honest, Mr. Cohen. It might be the way this professor teaches. She's very high level and does a lot of math in her head and stuff, but I swear that these problems don't feel like they're Calc 1 problems.
Well, the mere fact that we spent a half an hour doing the Riemann sum, yes. I would never do that. If I was teaching you calculus from scratch and I was putting together the curriculum, that would come at the end, not at the beginning.
Right.
And that's the toughest part. This U-substitution is a piece of cake compared to those summation notation formulas.
Well, and even that airplane problem is very tough.
Yes, it was. It was extremely tough. It threw me a little bit.
Yeah.
For a related rate problem, that's about as tough as they get.
Yeah, and it was. That was the first problem of the homework.
Yeah, that doesn't serve any purpose. Students should be started with easy problems and then medium problems, and then give them a tough problem after they've mastered the other two.
Yeah, exactly. So I don't know if that's the curriculum or the way the professor teaches it, but I'm sure that's over a lot of people's heads.
A lot of professors will teach straight out of the book, and most of the really good calculus books actually do it this way. They start out the toughest material is at the beginning. This calculus book that I'm using right now, it's got the Riemann sum definition long before you get the U-substitution or anything like that. It just doesn't make any sense to me why they do it, because it is like rocket science trying to figure out what the hell they're doing with that. Yeah, that's not the way to teach calculus. I really am a firm believer in easy, medium, hard, not the other way around. And yet math tends to do it the other way around, no matter what your subject. They did it with differential calculus. They did it to you with integral calculus. They did it to you with, they almost did it to you with limits. They didn't. They didn't force you to learn the delta epsilon definition of a limit, which is, you talk about tough.
Yeah. And
yet, if you go to the calculus book, that will be the starting place for limits, is that delta epsilon definition.
I don't know what, Calc 2 and Calc 3 hold, but to be frank with you, Mr. Cohen, the only thing, like knowing the 4 rules of derivatives is going to be something I retain. I'm not gonna retain the limit definition of a derivative. I just don't see any practice.
No, you probably won't ever need it again, except maybe one question on the AP exam or something. Are you planning on taking the AP exam?
No, not at this point. I don't see a reason for it. I mean, I just, when I think about what my job would be like, I just can't imagine in any facet that's the preferred method of a solution for any work, for any problem.
Yeah.
It's time consuming, it costs money and all of that. So, if I can get the right answer by not having to do the long way to do it, I'm assuming any boss or manager would prefer that.
Absolutely. Well, calculators and computers will do them all automatically for you anyway.
Right.
So we're in an age where, I don't know.
The code and the computers do the work for you. I think there is value in understanding what the background.
Yes, I do too. In the same sense that a person needs to know arithmetic, regardless of whether they have a calculator that'll do arithmetic for them.
Right.
If you don't know arithmetic, you are severely hampered in understanding all math beyond that. And I can't tell you how many students I get that just do not know arithmetic. They are 100% dependent on their calculator, and it just kind of freezes them in their tracks. They really can't really do algebra if they have to depend on that calculator. And it's the same thing with calculus. You may have a computer that does the integral, but you got to set up the integral. Right. In other words, from a real life problem, and in order to understand how to set up the integral, you really kind of have to know the harder way to do some of this stuff.
Yeah, you need to know conceptually what you're doing, and you need to have, a gist of the theory. And if you can get that, then there's programs that can do the work for you.
Yeah.
But it's meaningless if you don't understand the problem at a core level.
Yes. Yeah.
So on that note, Mr. Cohen, my dog's bothering me. He wants dinner time.
Okay. I will let you go.
I appreciate your time as always, sir. I will be contacting you soon.
Okay, Connor. Take care.
Have a good night.
You too.